Hello, everyone. Welcome to Regression Analysis. Today, we are going to see how data can help us understand relationships and make predictions. So, let's begin our journey into regression analysis. Now, let us understand dependent and independent variables using a very simple company example. Imagine a company has 100 different stores. The company wants to understand why sales are different from one store to another. So, for each store, the company collects some information. For example, how much money was spent on advertising, what price was charged, how much discount was offered, and how many days the company ran promotions. At the same time, the company also knows the actual sales of each store. Now, what is the company interested in? Sales. Therefore, sales is our dependent variable, or Y, because this is the outcome we want to understand and eventually predict. And what about advertising expenditure, price, discount, and promotional days? These are the independent variables, or X variables. They are the factors that we use to explain or predict sales. Now comes an important point. To build the regression model, we need data from our existing stores where both X and Y are known. Once we develop the regression model, suppose the company opens a new store. We may know the advertising budget, price, discount, and promotional days for that new store, but we don't yet know its sales. We can then give these new X values to our regression model, and the model will give us an estimated or predicted sales value. So, remember this simple sequence. Known X plus known Y, build the model, new X plus model, predict unknown Y. In very simple terms, X represents the information we use, and Y represents the outcome we want to predict. Now, look at our regression model. We already know the Y values and the X values from our observed data. But there is something we don't know, the values of the regression coefficients, such as beta 0, beta 1, beta 2, and so on. These coefficients have to be estimated from the data. So the question is, how do we estimate these coefficients? We want to find the coefficient values that make the predicted values of Y as close as possible to the actual observed values of Y. For every observation, there will be a difference between the actual Y and the predicted Y. This difference is called the residual. Now, some residuals may be positive and some may be negative. If we simply add them, they could cancel each other out. Therefore, we square each residual and then add all the squared residuals. Our objective is to find the values of the regression coefficients that minimize the sum of squared residuals. This method is called ordinary least squares, or OLS. So, in very simple words, we know X and Y. We estimate the regression coefficients, and we choose the coefficients that give us the smallest possible sum of squared residuals. That is the basic idea behind OLS estimation. Now we come to one of the most important assumptions of multiple linear regression, the assumption of linearity. We have already seen our MLR model, but before we apply and interpret this model, we need to ask an important question. Is a linear model appropriate for our data? In simple terms, we want to know whether the relationship between the dependent variable Y and the predictor variables X can be adequately represented by our linear model. We should not simply assume that the relationship is linear. We need to check it. So, how can we check linearity? First, we can use graphical methods. For example, we can examine residual plots. If the linear model is appropriate, we generally expect the residuals to be randomly scattered around zero, without a systematic pattern. We can also use a formal statistical test. One such test is Terres-Virta's neural network test for neglected nonlinearity. The basic idea of the test is that we start with the null hypothesis that there is no neglected nonlinearity in the specified model. If the p-value is greater than our chosen significance level, for example 0.05, we fail to reject the null hypothesis. This means that we do not have sufficient statistical evidence of neglected nonlinearity, and the linear specification may be considered adequate. On the other hand, if the p-value is less than 0.05, we reject the null hypothesis. This provides evidence that the specified linear model may be missing some nonlinear structure. Now, does this mean that we cannot model the data? No. We have several alternatives. We can consider nonlinear regression models, polynomial or interaction TERs, decision trees, support vector machines, or artificial neural networks, depending on the nature of the problem. So the important message is, first understand the data. check whether the linear specification is appropriate, then select and fit the appropriate model. We should choose the model according to the data, rather than forcing the data to fit a particular model. This is one of the fundamental principles of good statistical and machine learning modeling. Now let us discuss another important issue in multiple linear regression, multicollinearity. We know that in MLR, we use several independent variables to explain or predict one dependent variable. But sometimes, two or more of these independent variables are very strongly related to each other. For example, in our company example, suppose advertising expenditure and promotional days are strongly related. Whenever the company increases its advertising, it also tends to increase the number of promotional days. In this situation, these two predictors are providing very similar information to the regression model. This situation is called multicollinearity. Now, why should we be concerned about it? Multicollinearity does not necessarily mean that our model cannot predict Y. The bigger problem is with the individual regression coefficients. When predictors are highly correlated, it becomes difficult for the model to separate the individual contribution of each predictor. The coefficient estimates can become unstable, standard errors can become large, and interpretation becomes difficult. So, before interpreting our regression coefficients, we should check whether serious multicollinearity exists. One commonly used measure is the variance inflation factor, or VIF. The VIF tells us how much the variance of an estimated coefficient is inflated because of its relationship with the other predictors. The formula is VIF equals 1 divided by 1 minus r squared. We calculate this for each predictor by regressing that predictor on all the other predictors. As a simple rule of thumb, if VIF is greater than 10, we consider this an indication of serious multicollinearity. So, suppose our analysis gives a VIF of 15 for advertising expenditure. This tells us that advertising expenditure has a substantial linear relationship with the other predictors, and we should investigate the problem before interpreting its coefficient. Now, the important question is, what can we do if VIF is greater than 10? First, we should examine which variables are highly correlated. If two variables are essentially providing the same information, and there is a scientific reason to do so, we may remove one variable or redefine or combine them. But sometimes every variable is important and we don't want to remove any of them. In that situation, we can use regularization methods. Ridge regression adds an L2 penalty and shrinks the coefficients toward 0. Lasso regression uses an L1 penalty and can shrink some coefficients exactly to 0, which can also help with variable selection. Elastic net combines the L1 and L2 penalties and can be particularly useful when we have groups of correlated predictors. So, our overall approach is fit the model, check VIF. If VIF is greater than 10, investigate the predictors, choose an appropriate remedy, and remember one important point. Multicollinearity is mainly a problem for the stability and interpretation of individual regression coefficients. It does not automatically mean that the model has poor predictive performance. So, we should not simply look at VIF and immediately throw away the model. We need to understand the purpose of our analysis and then choose the appropriate solution. Now let us discuss another important assumption of multiple linear regression, the assumption of normality. First, let me clarify one very common misunderstanding. When we talk about normality in regression, we are not saying that our x variables or our y variable must be normally distributed. The normality assumption is about the error terms, or residuals, of the regression model. Remember our model, y equals beta 0 plus beta 1 x1 plus beta 2 x2 plus ... plus beta k xk plus epsilon. The error term represents the part of y that our model cannot explain using the predictors. Under the classical assumption, we assume that these errors are approximately normally distributed around 0. Now, why do we need this assumption? The normality of errors is mainly important when we want to perform statistical inference. For example, t-tests for individual coefficients, f-tests for the overall model, and confidence or prediction intervals, particularly when the sample size is small. However, I want to emphasize something important. Normality is not required for calculating the OLS coefficient estimates. So, how do we check normality? We can start with graphical methods. We can look at a histogram of the residuals and a normal QQ plot. In a QQ plot, if the residuals are approximately normally distributed, the points should lie reasonably close to the reference straight line. We can also use a formal test, such as the Shapiro-Wilk test, but we should not blindly depend on the p-value, particularly with large samples, because even very small departures from normality can become statistically significant. So we should combine the formal test with graphical examination and our knowledge of the data. Now, suppose we find substantial non-normality. What should we do? First, investigate the reason. There may be outliers, data entry problems, inappropriate transformations, or even model misspecification. Depending on the situation, we can consider a transformation such as log or square root transformation, a more appropriate model such as a generalized linear model, robust methods, or other alternatives. Another possibility is non-parametric or flexible regression. This becomes particularly useful when we don't want to impose a specific functional form on the relationship between x and y. In parametric regression, we specify a mathematical form, for example, a straight line. In non-parametric regression, we allow the data to determine the shape of the relationship more flexibly. Examples include kernel regression, Loess, and spline-based methods. So remember, normality in regression refers to the errors, not necessarily x or y. And if the assumption is not satisfied, we don't immediately abandon the analysis. We first understand why it is violated, and then choose an appropriate remedy or alternative model. Now let us discuss another important assumption of multiple linear regression, constant variance of the errors, which is called homoscedasticity. The opposite situation is called heteroscedasticity. Let us understand this with our company example. Suppose we are predicting sales for different stores. For small stores, our prediction errors may be relatively small, but for large stores, the prediction errors may become much larger. So the spread of our errors is changing as the level of sales changes. This is called heteroscedasticity. In simple terms, we can remember, homoscedasticity means constant spread of errors. Heteroscedasticity means changing spread of errors. So how do we identify it? First, we can use a residual versus fitted value plot. If the residuals have approximately the same spread throughout the plot, that supports homoscedasticity. But if the residuals form a funnel or cone-shaped pattern, where the spread increases or decreases, that is an indication of heteroscedasticity. We can also use formal statistical tests, such as the Breusch-Pagan test or the White test. The null hypothesis is that the error variance is constant. If the p-value is less than our chosen significance level, such as 0.05, we reject the null hypothesis and conclude that there is evidence of heteroscedasticity. Now, why is heteroscedasticity a problem? Under the usual exogeneity condition, the OLS coefficient estimates can still be unbiased, but the usual OLS standard errors may be incorrect. And if our standard errors are incorrect, our t-tests, f-tests, and confidence intervals may also become unreliable. So what can we do if heteroscedasticity is present? One option is weighted least squares, or WLS. Instead of treating every observation equally, WLS gives different weights to different observations. Observations with smaller error variance receive greater weight, while observations with larger error variance receive smaller weight. Another approach is generalized least squares, or GLS. GLS is more general. It can account for a broader variance-covariance structure of the errors, including unequal variances and correlations among errors. And if our main objective is valid statistical inference rather than changing the coefficient estimates, we can use heteroscedasticity robust standard errors, also known as Huber-White or sandwich standard errors. So our practical workflow is fit the model, examine residuals, test for heteroscedasticity, identify the cause, choose WLS, GLS, robust standard errors, or another appropriate remedy. The key message is heteroscedasticity does not automatically make OLS coefficients useless, but it can make the usual standard errors and statistical inference unreliable. So far, we have been discussing multiple linear regression, where our dependent variable y is continuous. For example, sales may be 10 lakh rupees, 15 lakh rupees, 20 lakh rupees, and so on. But now let's consider a different situation. Suppose a company wants to know whether a customer will buy a product or not. Here, our outcome has only two possibilities: buy equals 1, not buy equals 0. So our dependent variable is no longer continuous. It is a categorical variable. Now, Can we use ordinary linear regression here? No, not as our standard model. Why? Because linear regression can produce predicted values below 0 or above 1, but a probability can only lie between 0 and 1. Also, the assumptions we discussed for ordinary linear regression are not naturally suited to a binary outcome. Therefore, we need a different type of regression model. And one of the most important models for a binary categorical dependent variable is logistic regression. Logistic regression does something slightly different. Instead of directly predicting the value 0 or 1, it estimates the probability of an event occurring. For example, the model might tell us, probability that this customer will buy equals 0.82. So there is an 82% estimated probability that the customer will buy the product. We can then use a classification threshold, for example 0.5, to convert that probability into a predicted class. If the probability is 0.82, we classify the customer as buy. If the probability is 0.30, we classify the customer as not buy. Now, categorical dependent variables can come in different forms. If Y has 2 categories, we use binary logistic regression. If Y has more than 2 categories with no natural order, such as brand A, brand B, and brand C, we can use multinomial logistic regression. And if the categories have a natural order, such as low, medium, and high, we can use ordinal logistic regression. So, the important question before choosing a regression model is, what type of dependent variable do I have? If Y is continuous, we may consider linear regression. If Y is categorical, we need an appropriate categorical response model. The nature of Y helps determine the appropriate regression model. So, let us now summarize what we have learned about regression analysis. In very simple terms, regression analysis is a data-driven approach that helps us understand relationships between variables and estimate or predict an outcome using information available to us. And this is not something used only in statistics classrooms. Regression is used across almost every industry. For example, an IT company may use regression or related models to understand customer behavior and predict customer churn. A product or retail company may use it to predict sales based on price, advertising, discounts, and promotions. A bank may use predictive models to assess the risk of loan default. An automobile company can estimate the price of a used vehicle based on its age, mileage, and other characteristics. In agriculture, we can use regression models to understand or predict crop yield using rainfall, temperature, fertilizer, and other factors. So the applications are almost unlimited. But there is one very important lesson from today's discussion. There is no single regression model that works for every data problem. If our dependent variable is continuous, we may use linear or multiple linear regression. If our dependent variable is binary, we may use logistic regression. If we have categorical outcomes with multiple categories, we have multinomial or ordinal regression. If the relationship is nonlinear, we may need nonlinear or flexible models. And when we encounter problems such as multicollinearity or heteroscedasticity, we have appropriate methods such as ridge, lasso, elastic net, WLS, and GLS. So, how do we decide which model to use? I like to compare a data scientist with a doctor. A doctor does not give the same medicine to every patient. First, the doctor understands the symptoms, examines the patient, performs appropriate tests, identifies the problem, and then prescribes the appropriate treatment. A data scientist follows a similar approach. We first understand the problem and the data. We examine the characteristics and assumptions. Then we choose an appropriate model, estimate it, validate it, and finally use it for prediction or decision making. So don't start your analysis by asking, which model should I use? Instead, ask, what does my data tell me? And that is perhaps the most important lesson in data science. Right data, right model, reliable insights, better decisions.